He's going to tell us about universal transversality, or what I like to call transuniversality, with Bacon-Shor codes.
Yeah, thanks, Steve. And also thanks to Ken and Jake and the conference organizers.
Okay, yep. Right. Yeah. Then it doesn't go on.
All right. Well, hopefully that gave everyone time to shuffle in. Right, so I'm going to talk about universal transversality or transuniversality on these Bacon-Shor codes. Maybe turn that off. Oh, yeah. So, yeah, usually this term is reserved for some gauge fixing, where you convert between two related codes to exploit their complementary transversal gates. And you can think about this, what I'm going to talk about, the same way, except that you're converting between symmetric and asymmetric Bacon-Shor codes, which are related by a gauge as well. But if you want to think about it less sophisticatedly, I'm just going to explain how to do a controlled Z gate on Bacon-Shor. And so explaining this circuit is one of the main results of the talk. Okay, so let me begin by reintroducing Bacon-Shor. So the Bacon-Shor code is defined on a 2D lattice of qubits, and it's a stabilizer subsystem code. The gauge operators are just weight 2. So there's ZZ interactions between qubits in the same row and XX interactions between qubits in the same column. Logical operators are Z along columns. So this is a string of Pauli Z and a string of Pauli X's along a single row. So normally in this talk, we're going to often be focused on the Z gauge version of this, which just means that we take the Z gauge operators as stabilizers, and then the X type stabilizers are products of a bunch of these X gauge operators, all along a row. So denoted by this little schematic. So why should we be interested in Bacon-Shor codes? Well, they're actually one of the first codes discovered. And they're really simple to think about because you can just get them from concatenating two classical redundancy codes, one to correct bit flips and one to correct phase flips. And that also makes them simple to implement because you only have to measure weight 2 gauge operators. So coming along with this, this property is that you can initialize and do error correction by only making cat states. So basically, if you had a soup of cat states that you verified against errors, I guess, then you could do quantum error correction just from pooling cat states from that soup. Also, because they are 2D codes, they're great for experiments that are dimensionality constrained, like superconducting qubits. And they have a relation to the surface code as well. The surface code is one gauge of the Bacon-Shor code, and you can convert back and forth like this. Alaferis in his thesis also has an appendix about going from the surface code to the Bacon-Shor code by measuring some of the rows of qubits. Okay, so that's the introduction to Bacon-Shor codes, but what we're going to focus on is how to compute with them, and in particular, how to fault-tolerantly compute with them. Okay, but there are limitations to fault-tolerant computation for quantum codes and stabilizer codes in particular. For instance, the Easton-Knill theorem says that you cannot, for any transversal partitioning of the qubits, you cannot get a universal set of gates. So we have to compete with this if we want to get universal transversality. There are solutions in the literature, and one of the biggest ones is gauge fixing, which is where you use related codes that are different gauges of the same subsystem code And by converting between them, you get different gates. So for instance, on the color codes due to Bombin. So in our case, we can think about that as well by gauge fixing from symmetric Bacon-Shor codes to asymmetric Bacon-Shor codes. We get Hadamard here, and we get CCZ here, and that's universal. Or another solution is get rid of this unitarity assumption. So teleport in gates. Commonly, this is done with magic states. Like you use magic states when the gates you're teleporting in are not Clifford. But it's actually much simpler to do this if the gates you're teleporting in are Clifford. So codes that have transversal non-Clifford gates are actually privileged in this way because you can teleport in your Clifford gates like Hadamard just by using stabilizer states. And you also get to reuse the stabilizer state. So it's another nice property of codes that have transversal non-Clifford gates. And we'll see that asymmetric Bacon-Shor does have that. Okay, the second restriction is due to the Bacon-Shor code being a two-dimensional code, so it can be laid out on this lattice of qubits. Bravi-Koenig has a result that says local stabilizer codes in D dimensions cannot have local circuits for logical operators outside of the Deef level of the Clifford hierarchy. And then Petoskey and Yoshida have the same result for local subsystem codes with threshold. So we have to get around this, but also other people have to get around this when they make fault-tolerant gates on the surface code. And often, so one way is to look at non-constant depth circuits. For instance, when you do lattice surgery, usually this lattice surgery goes on for something like order D rounds. One of the first lattice surgery papers was by Horstman and others. But also you can look at non-local circuits. So if you allow non-local circuits and also non-local codes that have like stabilizers that are, that you have to measure non-locally. And this is what goes on in like these doubled or stacked codes. And I think Cody Jones, who is an author on the last one here, is going to talk about that tomorrow. So our construction is also non-local in a couple ways. Because the Bacon-Shor and the Z-gauge has non-local stabilizers, these big X-type ones. And also our circuit contains gates that span the lattice. So you might think that the non-locality of our circuit is all that's responsible here for being able to do a non-Clifford gate. But that's actually not true. So the asymmetry in the Bacon-Shor code is actually important as well. So let's think about an example. So why do we need asymmetry? And this is an example and ongoing work in preparation with Thomas and Alex. So the result, at least the intuitive result, is even with non-locality, if you have a symmetric code, then you have to have a symmetric 2D code, means that the gates you can implement are still going to be restricted to Clifford gates. Okay, so here we have like an M by M lattice of qubits, let's say. Yeah, you can think of this as a surface code or as a Bacon-Shor code. And one of the logical Pauli operators is this string here. This string has support order M. If we act on it with our non-local circuit U, the region that this commutator has support on should also be order M, right? Because this circuit is constant depth, and it can only spread out G1 to an order M sized regions. But if we look at another logical Pauli operator, it has, here's one representation of another logical Pauli operator. It may intersect this commutator UG1 in an order M region. So then we can say nothing about the double commutator. Like the double commutator of UG1, G2 could also be order M. But G2 also has equivalent representations, logically equivalent representations, that must not intersect UG1 in more than a constant size area. Because if UG1 intersected all of these representations in a non-constant size area, then UG1 must be a non-constant times m. There are m equivalent representations of G2 size. So in this way, we can find a G2 prime such that this double commutator is in a constant size area. And if it's in a constant size area, it must be the trivial logical operator. And if the double commutator is trivial, then U is Clifford. Okay, so this chain of arguments about just the supports of operators can show that even with non-locality, you must have Clifford gates. Okay, but why does asymmetry solve this problem? So if you have an asymmetric code, then one of your logical operators is order m squared. So on an m squared by m code. And if it's order m squared, it can get mapped by U to an order m squared region. And now this order m squared region, there's no way to find a representation of this same logical operator that does not intersect this region in at least order m places. So we can't make the same argument as before. And in fact, well, the Bacon-Shor code gives an example of why this argument must fail. So this is one way that you could distribute UG1, but we could also distribute UG1 this way. And then this makes it clear that the gate range you need is at least m, this dimension, because we have to map this operator at least up order m distance. Okay, so that's why asymmetry is important. And also why the non-locality of the circuit's important. So here's our main result, our circuit for transversal CCZ on asymmetric Bacon-Shor. The lines here, the colored lines, are physical CCZ gates. And the qubits are differently sized and colored depending on what code block they're in. I hope the code block C might be a little dim, but you should be able to tell where they are by where the lines end up. So there are, in total, m cubed physical CCZ gates. And each physical CCZ gate, each qubit in the code is involved in at most one physical CCZ gate. So this circuit is actually all depth 1, which means it's transversal. So this m squared by m Bacon-Shor code has a transversal CCZ. Likewise, you can get controlled k qubit controlled Z gates on m by m to the k codes. So to see why all of this works, I'm going to run through like the sketch of the proof. Okay, so it shouldn't be too difficult, I hope. So it begins with this round robin trick for implementing logical gates. And this is something I worked on with Ryuji and Ike, my advisor at MIT. And so basically we want to make logical CZ between two different code blocks. This is code block A and code block B. And to do that, we look at the support of logical Z on both of these codes, and we connect every qubit in the support of logical Z on the first one to every qubit in the support of logical Z of the second. So we just, these are CZ gates in all the different, between all the different pairs of qubits. Okay, and the claim is that this does logical CZ. Okay, so how can you prove that? Well, each code block is a stabilizer code, we're assuming. So logical Z is some string of Paulis. We can do a Clifford gate to make the string of Paulis all Zs. Okay, and do the same thing down here. So now logical Z in this locally Clifford equivalent code is just a string of z's. So to do logical CZ, we'll write the value of z bar from this first code into an ancilla. So this first part of the circuit results in an ancilla that is 1 here, if and only if the logical qubit is in 1 bar, so in the logical 1 state. And then we'll write, we'll use the value of the ancilla to do logical z down here. Okay, so we'll just apply logical z to the lower code, and then we'll erase the value from the ancilla. So this is a circuit to do CZ. It's not like, I mean, it uses an ancilla, and it's obviously not fault tolerant and all. But so we'll change the circuit up. So the first step is to commute this gate through this gate. And when you do that, you get another CZ gate. So this is the only circuit identity you need to know. When you pull a C0 through a CZ, you get a new CZ from the controls of the two. And it doesn't matter which order these are in because the new CZ commutes with those original 2 gates. And so you just keep doing this until you get 3 new CZ gates. The original CZ is now over here, and it's controlled on 0, so it disappears. So we can get rid of that. And then we do the rest with the other gates. Eventually, these C0s come over here, and they annihilate with these C0s. And we're left with this circuit, where we connect every qubit in the support of Z up here to every qubit in the support of Z down here. And this is what we call the round-robin construction. The ancilla has completely disappeared from the circuit. Okay, so that's how you do CZ. That's the proof of CZ. But you can also do CCZ this way. And I'll leave that as an exercise, I guess. It's just the same argument. So logical CCZ, you connect every qubit in the support of Z bar on 3 code blocks now to every other. So there are now D-cubed CCZ gates this way. And the reason we're interested in CCZ is because it's computationally universal paired with H. And H is really easy to implement either by state injection or if your code naturally has transversal H, like many self-dual CSS codes do, or all self-dual CSS codes. Okay, right. So what I want to say about this circuit is it's not fault tolerant as it is. You can make it fault tolerant in a couple ways. You can do error correction in between some of the gates, so break it up into transversal pieces, actually. We're not going to do that here because there's a simpler way by exploiting the symmetry of the Bacon-Shor code. So by symmetry, I mean the symmetry of the code space, which basically reduces to the stabilizers. Okay, so we're going to use the stabilizers of the Bacon-Shor code to simplify our round-robin circuit. So here's the round-robin circuit using the lines representing CZ gates as before. So it's a complicated mess just on the support of Z bar over here on the left. But then the stabilizers say that within one row, the value of these 2 qubits are always the same, right? So the eigenvalue of ZZ is always +1. But that also means that if we apply controlled ZZ from a qubit ancilla qubit, this is also acting as identity on the code space. So we can use this to our advantage because, okay, let's just look at all the CZ gates from this first qubit. And let's say we want to target this red one, the one in the middle, and move it around. So we can use this circuit, which is identity, and use it between these 3 qubits, using this as the ancilla, and these 2 as the members of this stabilizer here. And then what effectively happens is the CZ gates here cancel, and we move the CZ over. Okay, so we can move CZs around using the stabilizers. We can do that for this CZ gate as well. And then we can do it for all the CZ gates in the circuit. And what we end up with is a transversal circuit. We can just shift the nodes of the CZ gate and spread them out over the columns of the Bacon-Shor code. So CZ is transversal on these symmetric Bacon-Shor codes. It's also transversal on the asymmetric ones. But we need the asymmetry here because we have a lot more CCZ gates to spread out. We have m squared CCZ gates for each qubit here, so we need an m squared width code. And so that's how the asymmetry helps us like more directly to do this transversal CCZ gate. Okay, so that's the main construction of the talk, and it's how we get our simple non-Clifford gate for these Bacon-Shor codes. So now I want to move on to more like practical issues, like how will you actually implement a Control-Z gate on Bacon-Shor codes in sort of the near future? And how will you universally compute with these Bacon-Shor codes? So so some of the very basic primitives of computation are initializing states, like initializing plus states and initializing 0 states. And so we can do that. We can initialize logical plus states and logical 0 states just by making cat states. This is sort of one of the advantages of using Bacon-Shor is that to make logical plus, you just make these cat states, these n qubit cat states, and you do it m times. And then you get an m by n Bacon-Shor code. And you can do the same thing to encode logical 0. This is in the Z gauge, and this is in the X gauge. Okay. Also, when you want to do error correction with the Bacon-Shor code, you just use cat states as well, because you use these logical states to do Steen error correction. And you don't even need to repeat this, so it's just one-step error correction. So for a single 3x3 code block, you would use like 18 qubits here to do everything you need with that single code block, error correction included. Also, when you want to measure your logical states, you can do this transversally as well. So you can just, if I want to measure logical X, then I measure all the qubits in X. And if I want to measure logical Z, then I measure all the qubits in Z. So preparation and measurement are very simple, and error correction is very simple. The CCZ gate looks complicated because it's on 3x9 qubits. So how can we simplify that? Well, do we really need the whole asymmetry of the code? So if you remember from the proof, the asymmetry just allowed us to move the CCZ gates out and spread them out over the whole code. But if we just have a 3x3 code, then we can't spread the CCZ gates out all the way, but we end up with a depth 3 circuit instead. So here I'm writing a depth 3 circuit, and I'll explain all the notation. Now that depth 3 circuit is not obviously fault tolerant, but if you do the appropriate error correction afterward, then you can make it so. Okay, so what is the circuit? Well, I'm showing, if we partition these 3 Bacon-Shor code blocks into regions 1, 2, and 3, then this picture is showing these regions 1, 2, and 3 and what happens to them as time goes on. This circuit C0, well, it corresponds to time step 0. It's just some circuit of CCZ gates on these 9 qubits. Same with C1 and C2. So we apply those throughout time on region 1. Region 2 is the same thing, except there's a permutation of the circuit that goes on. It's not really important what the permutation is. It's like a cyclic permutation of block A and the same cyclic permutation inverse on block C. But this is what we do to region 2, and then region 3 is the same thing, except the permutation is squared. Right, so we do this circuit, and this does logical CCZ, but then we have to do error correction. And this is where we do something a little different than normal stabilizer codes. Because normally in stabilizer codes, you would measure all the stabilizers here, and then you would apply some Pauli correction, right? But that's not all you can do. So in fact, that's a very limiting form of the Knil-Laflamme conditions, which say when a channel is correctable. I mean, it's more limited than what the Knil-Laflamme conditions would say is generally possible. So in fact, the errors that we get from circuit noise in this channel can be corrected if we measure the Z-type gauge operators first, and then do recovery that consists of X and CZ gates. And then we measure the X-type gauge operators and do recovery that consists of Z gates. Okay, so it's this two-step error correction, and it's also involving some non-Pauli recovery operators. And this can make the circuit fault tolerant to one gate fault. Just to demonstrate some of the tricks that should probably be used in small experiments, because this greatly reduces the number of qubits we need from 3 by 9 to 3 by 3. This simple trick. Okay, so the next thing I want to talk about is actually more like overhead and threshold calculations for this scheme. And in particular, I'm going to be using the MusicCue architecture created by Chris Monroe here at Maryland. So I wanted to fix an architecture just because I want like actual times for gates and the length of a whole like error correction cycle. So these are the idealistic times that are in this MusicCue paper. Ideally for single qubit gates, we could do them in 1 microsecond. 2 qubit gates, 10 microseconds. Same with 3 qubit gates. And initializations on par with single qubit gates, and measurements sort of the longest task, which is like 3 times a 2 qubit gate. But the general layout of this MusicCue architecture is actually very good for the Bacon-Shor code, because remember we have these non-local operations, which isn't great for hardware that is constrained in like a plane, say. But the MusicCue architecture has these interconnects between different ion traps, and through these photonic interconnects, you can interact qubits from different ion traps, and you can also, within a single ion trap, you can do gates sort of non-locally. So this is how we could do our non-local CCC gates, if this thing existed. There are plans, you know. The ideal numbers are like 100 qubits per ELU, and half of those should be communication qubits used for entanglement between the different ion traps. Okay, so using these numbers, we can estimate overheads. So here's an overhead comparison between magic states on the 7 qubit code, magic states on the 9 qubit code, and also our 3 by 3 Bacon-Shor. So the circuit volume metric here is just a count of the number of gates in the circuit, and then you weight them by the number of qubits in the gate. So you would count a 2 qubit gate would be counted twice, and like a 3 qubit gate would be counted 3 times. So we see a drastic improvement in circuit overhead over these magic state schemes. The magic state circuits are shown right here. This is how you prepare a magic state by measuring this Clifford operator twice. And this is how you use that magic state, the CCZ state, to inject CCZ on psi. So these are just the explicit circuits here. We see about like 2 to 3 times improvement over these. The space-time metric is similar, except now we're actually using the times from the MusicCue estimates. The total time is just, well, the time component of the space-time metric. And the qubit is sort of the space metric, or is the space dimension from the space-time metric, except that we're allowing qubit reuse. Yeah, so we see improvements in all of these by using our optimized Bacon-Shor 3x3. Okay. Right. And so the next thing are these pseudo thresholds for our scheme. Yeah, so these pseudo thresholds are calculated in the XREC formalism, which means that we do some leading round of error correction, and then we do our controlled Z gate, that depth 3 circuit that I showed before, and then we do the final round of error correction. And here are the gate noise models. So the thresholds on the left were calculated using this one, where a 3-qubit gate, a 2-qubit gate, and a single qubit gate are all fail with the same probability P. And the right weights the 3-qubit gate more, like the 3-qubit gate fails with 10 times the probability of a 2-qubit gate and 100 times the probability of the single qubit gate. The thresholds we get are pretty optimistic, at least for like the XREC formalism. So I'll show a comparison to the magic states next. This plot shows the logical error rate divided by the leading order, so that we extract the leading constant, at least divided by 1,000, I think. Yeah. And here's the identity gate, and here's the identity gate for the surface code, 17-qubit surface code. So already the Bacon-Shor is improving over that. And the reason that's true is because here we're using Steen error correction, which is really easy for the Bacon-Shor code because, again, you just make cat states. Whereas that's something that's not easily available for the surface code.
Sorry, I don't understand this graph.
Yeah.
Explain the axis again.
Right. So this is the logical error rate, but then you're dividing out the leading order. The leading order in this case is p squared, the physical error rate p. And then also dividing by this 10 to the 3 just to make the numbers on the left.
And what are the two lines?
Right. So when we do our XREC calculations, we're actually getting upper and lower bounds as polynomials in P. So we calculate everything exactly. There's no Monte Carlo. So we just look at all 2 fault paths. So every combination of 2 gate failures, and just by looking at that, you can get upper and lower bounds on the logical failure probability. Okay. So these are the upper and lower bounds. And then with those upper and lower bounds, you can get upper and lower bounds on the threshold, which is where it crosses P. This line P logical equals P. And here are shown the lower bounds. So these are the more pessimistic pseudo threshold. Like the pseudo threshold is somewhere in this range, and we just report the lowest. Okay, that makes more sense. Yeah, here is the same plot, but with the 7-qubit magic state pseudo threshold, which is actually worse by about a factor of 4, or at least the constant in front of the constant of the leading order term is a factor of 4 larger. And thanks to Ryuji for doing this calculation. The error model on the right is, well, as I explained before, weighting multi-qubit gates as failing more often. and we get similar pseudo-threshold results. They're actually a little better because most of the gates in the circuit are actually not multi-qubit gates. Most of the gates are two qubit gates or single qubit gates. In fact, there's a lot of single qubit gates that are just identity gates, like the qubit is just idling. So making that fail less improves these pseudo-thresholds, or at least improves the CCZ one, I guess, or these larger circuits. Yeah, I think I'm going to have a lot of time for questions, actually. This is my final slide. So the small code problem is something I want to point out as an important problem in the very near future as people start implementing these codes in like the MusicCue program or just the various companies that have grown up have appeared to do quantum computing, or at least say they're going to do quantum computing in the near future. So the basic question is we're going to look at distance 3 codes, and because these are the codes that will first be implemented, and ask what is a good distance 3 code. It doesn't have to perform well, as some part of a code family as distance goes to infinity or whatever. But we want very few qubits because we only have a few. And we want error correction to be fast and efficient. We want logical gates that are easy, like transversal gates. And ideally, you want a universal set of gates. Now, you can't do them all transversely. But somehow, we want an easy set of universal gates. And you also want a pseudo-threshold that is high, not an asymptotic threshold that is high. Ideally, you would also have some way to do logical tomography well, so that you could benchmark your experiment. The claim is that BaconShor satisfies at least these first 5, and maybe the 6th if you expand your definition of tomography. So the BaconShor code, I think, is a good place to start here as a small code. Can be implemented in the near future and show that quantum computing, or at least fault-tolerant quantum computing, is possible. Of course, what makes a good code is a question that depends on your hardware. BaconShor, or at least the Bacon-Shor CCZ, might not be for everyone. You have to be able to do non-local gates, like say in MusicCue, or maybe some of these photonic architectures. And it's also an application-dependent question, because what fault-tolerant gates you need depend on what algorithm you want to run. Like Shor's algorithm uses a lot of classical Toffoli gates, for instance. So some gates are more important than others. Okay, so I'm going to leave it there and take questions.
Thanks for a wonderful talk, Ted. We have some time for questions.